Hey everyone, so in class 80 we were using Snell's law, just practicing with it a little bit. So first question here says a ray of light with a frequency of 5.09 times 10 to the 14 hertz traveling in medium x is refracted at point P. The angle of refraction is 90 degrees as represented in the diagram. So we can see the diagram over here to the right. The first question we don't need the diagram for. It says calculate the wavelength of the light ray in air. So to find wavelength, our only equation with wavelength is our equation V equals F lambda. So if we start with that, so it's light in air, so we know its speed is 3 times 10 to the 8th meters per second. Our frequency is given to us 5.09 times 10 to the 14 hertz, and we're looking for wavelength. So if we throw this in our calculator solving wavelength, we have to divide both sides by 5.09 times 10 to the 14th. And we get a wavelength equal to 5.89 times 10 to the negative 7 meters. All right. So for the next one here, it says measure the angle of incidence of a light ray at point P and record the value, label the diagram. I don't have a protractor in front of me, so I'm just kind of eyeballing this. It looks like it's about 50 degrees. So the angle of incidence is this angle right here. That's the angle we want, and that looks like to me to be about 50 degrees. It's definitely more than 45. So to get the index of refraction, we got to use Snell's law. So our angle of incidence, that's theta 1, is 50 degrees. Our angle of refraction was given to us at the beginning. That's 90 degrees. Where is that exactly? Might be hard to see here. It's up here. Okay, that is our theta 2. So this is theta 1. This is theta 2. Our first index of refraction now can be confusing. Remember, you always go into N2, so we're going into air. So we'll write N2 first. That's air, so that's 1. N1, that's medium X, we don't know. So setting up Snell's law. N1 sine theta 1 equals N2 sine theta 2. So we have 1 sine 50 degrees, don't forget to include the degree symbol there, equals N2, excuse me, I gotta go back a little bit, I made a small mistake there. N1 is actually our unknown. N2 is 1, and sine of 90 degrees, don't forget the degree symbol. So the math here is actually pretty simple because this whole side on the right is equal to 1 because sine of 90 is equal to 1. So that whole side is 1. So to find N1, it's just 1 divided by sine of 50. Which comes out to be 1.305. Now, this question might look a little bit different. What you'll notice is that actually the interface is going the other way. So we have the unknown material on the left and air on the right. And our normal line is perpendicular to the two there. So if we look, it says a ray of light. Now that frequency of 5.09 times 10 to the 14th hertz, that's kind of like a standard frequency we usually see. You don't necessarily have to use it for the question. You might, but in many cases you don't. Let's see. It looks like our angle of incidence, that's theta 1, is 30 degrees. How do I know it's theta 1? Because that's the first material. We're going left to right. So the first material has an angle of incidence of 30 degrees. So the first thing you have to do is find the angle of refraction. That's this angle right here. That's theta 2. And again, I don't have a protractor on me right now. It's kind of hard to use on this screen. But just kind of eyeballing it, it looks like it's about 60 degrees. It's definitely more than 45, definitely less than 90. So calculate the index of refraction of the unknown material. So the unknown material is N1. N2 is always the material we're going into. That's air, so that's 1. Theta 1 is 30 degrees. Theta 2 is 60 degrees. So using Snell's law again, N1 sine theta 1 equals N2 sine theta 2. We have N1 sine of 30 degrees equals 1 times the sine of 60 degrees. Now solving for N1, basically what you end up doing is sine 60 divided by sine 30. And we get about 1.73 as our N1 value. Now, it's always a good idea to think, does this make sense? Well, we notice here that this is a problem where the angle of refraction is bigger than the angle of incidence. So that tells us that N1 has to be bigger than N2. Okay, because we go from a high index of refraction, in this case 1.73, to a lower index of refraction, in this case 1, the light's going to bend away from the normal. It's going to have a bigger angle of refraction, and it does in this case. So now we have to look at the picture for most of our information here. So let's see what we have. It says light travels from lucite into another material. The angle of incidence is 32 degrees. The angle of refraction is 16 degrees. There's a lot of information there, and it might be a good idea to get all your givens listed right away. So from lucite into another material. So N2s are unknown. Lucite has an index of refraction of 1.5. Theta 1 is 32. Theta 2 is 16 degrees. Did the light bend toward or away from the normal? Notice here, the normal line is the dotted line. We're going from left to right, from lucite into the mystery material. So it looks like, let's see, the angle of incidence is 32 degrees, the angle of refraction is 16 degrees, so we got closer to the normal, so we went toward. Therefore, this must be a low n to high n problem, a low index to high index problem. The reason being low to high is always toward the normal. So let's use Snell's law to figure out what exactly N2 is equal to. Now to solve for N2, in your calculator, you can do 1.5 times the sine of 32 degrees. Let me just do that in my calculator. 1.5 sine of 32 divided by, because you have to divide both sides by the sine of 16 degrees, so divide by the sine of 16. We get 2.88. Does this agree with our prediction? Yeah, it does, because we predicted that we were going into a higher index of refraction, and we are. So yes, N2 is bigger than N1, which is what we predicted. So again, I don't have a protractor on me, so I'm just going to eyeball it for this one. So we have to measure the angles and put them in the givens area. So just to eyeball it, theta 1's on the left because we're going, if you follow the arrows, we're going from left to right. So we'll say that this is about 30 degrees. We'll say that this is about 10 degrees. Could be off a little bit there, but that's ballpark what they should be. You should be a little bit more accurate than that, though. And it looks like we're going from air into missing material. So N1 is going to be 1 because that's air. And again, we don't know N2. All right. So light is bending blank the normal. So let's see. The light is coming in at 30 degrees and it's refracting at 10 degrees. So it's getting toward the normal. So this must be a low N to high N problem. And it has to be a higher index of refraction. Nothing's going to have a lower index of refraction than air, which is 1. You can't go lower than 1. So it's Snell's law. So on the left side, 1 times sine of 30 is 1/2. Divide both sides by sine of 10. And we get, again, about 2.88. Now that's just a coincidence, but it should be a pretty similar answer to the previous one. So is our prediction correct? Did we go into a higher index of refraction? Yes, because N2 is greater than N1.